Something unusual just happened in AI development that nobody saw coming. While most companies are racing to build bigger models with more training data, Google just released Vista, a system that doesn't need more training at all. It gets better by watching itself fail, critiquing what went wrong, and trying again. The results? It's beating Google's own flagship video generator 60% of the time, and the gap keeps widening with every iteration it runs. This isn't just another incremental upgrade to video generation. This represents a fundamentally different approach to how AI systems improve themselves, and the implications reach far beyond making better YouTube content. Traditional AI video generators operate on a simple principle. You feed them a text description, they process it through billions of parameters trained on millions of videos, and they output whatever the model thinks matches your request. If you don't like the result, you either accept mediocrity or craft a better prompt and start over. The model itself never learns from the specific failure. It can't examine what went wrong, understand why, and correct course. It just generates and hopes. Vista flips this equation completely. When you give it a video concept, the system doesn't immediately start rendering. Instead, it enters what researchers call a planning phase, where it deconstructs your idea into granular components. Every scene gets broken down into 9 distinct properties that define exactly what should appear on screen and when. Duration determines how long each segment lasts. Scene type classifies whether it's dialogue, action, establishing shot, or transition. Characters identifies who appears. Action specifies what they're doing. Dialogue captures what they're saying. Visual environment describes the setting and background. Camera work defines angles, movement, and framing. Sounds outlines audio elements from ambient noise to music. Mood establishes the emotional tone. This level of detailed planning creates something crucial, a concrete reference framework that later iterations can optimize against. Instead of vaguely hoping the next attempt will be better, Vista knows exactly which elements succeeded and which failed across multiple specific dimensions. Once planning completes, Vista generates not one video, but multiple candidates, typically around 30 per iteration cycle. These candidates then compete in what the research team calls a tournament structure. Videos face off in pairwise comparisons, winners advance, losers are eliminated. But here's where it gets genuinely clever. Before any comparison happens, the system generates what it terms probing critiques for each video. The AI examines every candidate first, analyzes its strengths and weaknesses, builds an understanding of what quality looks like in this specific context, then uses those insights to make informed comparisons rather than arbitrary judgments. Think about what this means for a moment. The system isn't just picking videos that feel better. It's developing analytical frameworks for understanding quality, then applying those frameworks consistently across all candidates. This transforms subjective aesthetic judgment into something approaching systematic evaluation. After the tournament crowns a winner, that video faces its toughest test yet, the jury system. 3 specialized judges examine the winner across 3 distinct dimensions: visual quality, audio quality, and contextual accuracy. Within each dimension, there's a hierarchical structure deliberately modeled after legal decision processes. A standard judge scores the video on established metrics. An adversarial judge actively searches for flaws, attempting to poke holes in the quality and identify problems the standard judge might overlook. A meta judge then synthesizes both perspectives, weighing their competing assessments to reach a balanced conclusion. This multi-judge architecture exists because single perspective evaluation consistently misses issues. One viewpoint might find a video acceptable while another immediately spots temporal inconsistencies, audio sync problems, or physical impossibilities. By forcing multiple viewpoints into conversation, including one specifically designed to find faults, Vista catches errors that simpler evaluation systems routinely miss. The metrics these judges apply are extraordinarily comprehensive. Visual evaluation examines fidelity, motion dynamics, temporal consistency across frames, camera focus quality, and visual safety. Audio assessment covers sound quality, audio-video synchronization, and audio safety. Context analysis checks whether situations make sense, whether meaning remains coherent, whether visuals match text descriptions, whether physics behaves realistically, whether the content engages viewers, and whether video format elements like openings, closings, and transitions flow smoothly. After comprehensive critique across all these dimensions, Vista activates its deep thinking agent to rewrite the original prompt. This isn't cosmetic editing. The agent works methodically through 6 reasoning steps before proposing any changes. First, it identifies specific failures based on which metrics scored poorly. Second, it clarifies what success should actually look like for those elements. Third, it verifies whether the current prompt contains sufficient detail to achieve that success. Fourth, it determines whether failures stem from model limitations or inadequate instructions. Fifth, it detects conflicts, ambiguities, or vague language that might confuse the generator. Finally, it proposes targeted modifications addressing each identified problem. Only after completing this entire analytical process does the system generate new prompts. Then the cycle repeats. New videos get created from refined instructions. The tournament selects the best candidate. The jury delivers fresh critiques. The deep thinking agent rewrites prompts again, incorporating lessons from the latest failures. By default, Vista runs 5 complete iterations, 1 initialization plus 4 improvement cycles. Each iteration samples 5 prompts with 3 variants each, generating 2 videos per prompt. That's 30 videos per iteration, 150 total across the full process. The computational cost is substantial, consuming roughly 700,000 tokens per iteration, with most spent on tournament evaluation, where each video input exceeds 2,000 tokens, but the performance gains justify the expense. Benchmark testing reveals the magnitude of improvement. Researchers tested Vista against direct prompting, simply feeding raw user requests straight to the generator with zero optimization. By the 5th iteration, Vista was winning 45.9% of single-scene comparisons and 46.3% of multi-scene tests. The gap between wins and losses hovered around 32 to 35 percentage points. That's not marginal improvement. That's categorical difference in output quality. They also tested Vista against other optimization approaches like Visual Self-Refine, Google Cloud's rewrite tool, and VEO. Those systems showed inconsistent results, sometimes even degrading with additional iterations. Visual Self-Refine started strong but quickly plateaued. VEO and rewrite fluctuated randomly without clear improvement trends. Vista, by contrast, improved steadily with every iteration, compelling evidence that it's genuinely learning rather than randomly stumbling into better outputs. Human validation confirmed the automated metrics. 5 expert annotators experienced in prompt optimization compared Vista's results against the best competing models after 5 iterations. Vista won 66.4% of those head-to-head evaluations. When experts rated full optimization runs on a 1 to 5 scale, Vista averaged 3.78, while the next best baseline scored only 3.33. Looking at specific metrics, Vista boosted visual quality scores from 3.36 to 3.77, and audio quality from 3.21 to 3.21, 3.47. One particularly revealing test involved pushing Vista to 20 iterations instead of 5. Performance continued climbing steadily while the best baseline plateaued and became noisy around iteration 7. This suggests Vista's improvement ceiling extends far beyond the default settings, limited primarily by computational budget rather than algorithmic capability. The system also handles a persistent problem in video generation: hallucinations. Most video models occasionally generate elements nobody requested. Random text overlays appearing spontaneously, music playing when none was specified, objects materializing or vanishing impossibly, characters moving in physically nonsensical ways. Vista dramatically reduces these errors by enforcing strict constraints during planning and applying penalties during selection when videos violate those constraints. Unless users explicitly request captions, Vista penalizes any video containing them. Same principle applies to music, voiceovers, and physically impossible movements. This filtering eliminates much of the weirdness plaguing other generators. Real-world instruction following tests demonstrate the practical impact. In one example, researchers requested a factory scene containing a blade battery on a conveyor belt, a yellow industrial robot, and a screen displaying a yield percentage in simplified Chinese. Direct prompting either omitted the robot entirely or generated incorrect text. Vista executed all 3 elements perfectly. Another test requested gremlins on a wooden roller coaster moving forward while the camera tracked backward, a complex coordination of subject and camera motion. Direct prompting generated gremlins inexplicably moving backward at absurd speeds, creating visually ridiculous and physically impossible footage. Vista produced exactly what was requested: gremlins forward, camera backward, everything smooth and coherent. These aren't trivial improvements. They represent the difference between content you can actually use and content you immediately delete. Vista fits into a broader transformation happening across AI research right now: test time optimization. Instead of making models bigger or fine-tuning them on specialized datasets, you invest computational resources at inference time to search for better outputs. The same principle powers reasoning models that solve complex problems by thinking longer before answering. Vista applies this concept to video generation, becoming the first black box test time prompt optimization framework specifically designed for visual media. Previous methods either required white box access to model internals or focused narrowly on specific aspects like object presence. Vista jointly optimizes visual, audio, and contextual dimensions simultaneously in one unified loop. The system has limitations. It depends on multimodal language models as judges, which can introduce bias. Human evaluations help balance that bias but don't scale economically. The quality metrics assume certain creative styles that might not fit every context. Performance depends fundamentally on underlying model capabilities. Vista can only squeeze out improvements the base generator can actually produce, but within those constraints, the results speak unambiguously. Vista beat V 3 in 60% of tests, won 66.4% of human evaluations, showed steady improvement with each iteration, reduced hallucinations, improved instruction following, handled multi-scene videos more smoothly, and maintained audio-visual synchronization, all at test time without any retraining. For media production, marketing, education, and entertainment, this represents a massive leap forward. Self-optimizing video generation can dramatically reduce production costs, accelerate workflows, and enable content scaling previously impossible. The question isn't whether this technology works. The question is how far it can evolve.